Hey everyone, and welcome back to the channel. Today, we're tackling LeetCode problem number 46, permutations. This is a medium difficulty problem, and it's a classic that often shows up in coding interviews. The goal is simple. Given an array of distinct integers, return all possible permutations of those integers. For example, if we input the array 1, 2, 3, we should get back a list of lists containing all possible orderings. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. Seems straightforward, right? But the challenge lies in efficiently generating all these permutations. We'll explore different approaches, starting with a naive brute force method and then moving towards a more efficient solution. Let's dive in. Understanding with examples. Let's solidify our understanding with a few more examples. If the input is 1, the output is simply plub1. If the input is 1, 2, we get plub1, 2, plub2, 1. Notice a pattern? For each element, we need to consider all possible positions it can occupy within the permutation. Now consider 1, 2, 3. Starting with 1, it can be at position 0. Then we need to find all permutations of 2, 3, which are 2, 3, and 3, 2. This gives us 1, 2, 3, and 1, 3, 2. Next, let's put 2 at position 0. We then permute 1, 3, getting 2, 1, 3, and 2, 3, 1. Finally, with 3 at position 0, we permute 1, 2, getting 3, 1, 2, and 3, 2, 1. See how this systematically generates all possibilities. This intuition will guide our efficient approach later on. Let's now look at a brute force way to achieve this. Brute force approach. A naive approach would be to use nested loops to iterate through all possible arrangements. Imagine 3 nested loops for an input array of size 3. This would generate all possible combinations. While this works for smaller inputs, it becomes computationally expensive. The time complexity grows factorially, O of n factorial. This means the runtime explodes as the input size increases. For larger arrays, this is simply not practical. It's not very efficient for larger inputs, so we need a smarter, more efficient algorithm. Optimal solution. The optimal solution involves a technique called backtracking. Imagine building the permutations step by step. We'll use recursion. We start with an empty permutation. Then, for each element in the input array, we try placing it at every possible position within the current permutation. Once we've exhausted all positions for that element, we backtrack. That is, we remove the element and try the next one. This recursive exploration systematically generates all possible arrangements without redundant computations. This backtracking approach dramatically improves efficiency. Code implementation. Let's see the code in Python. We'll define a recursive function that takes the input array and the current permutation as input. The base case is when the current permutation has the same length as the input array. In this case, we've found a permutation and add it to our result list. Otherwise, for each element in the input array, we check if it has already been used. We'll keep track of this. If not, we add it to the current permutation, recursively call the function, and then remove it to backtrack. This ensures we explore all possibilities. We'll then return the list of all permutations. Time and space complexity. The time complexity of our backtracking solution is O of n factorial, which is unavoidable because we have to generate all possible permutations. The space complexity is also O of n factorial in the worst case, because in the worst case, we have to store all the permutations in memory. However, we can say that it is linear, or O of n in the recursive depth, in terms of stack space usage. The space complexity to store the permutations in memory, however, is O of n factorial. This is a significant improvement over the brute force approach, which would have even worse space complexity. Engagement break. So, what did you think of that solution? Did you find it helpful? Let me know in the comments below. Also, don't forget to like this video if you found it useful, and subscribe to the channel for more LeetCode tutorials like this one. And if you have any questions or suggestions for future videos, just leave a comment. I would love to hear them. Let's now look at the conclusion. Conclusion. In this video, we tackled LeetCode problem 46, permutations. We started with an understanding of the problem, explored a naive brute force approach, and then implemented an efficient backtracking solution.